Hello everyone, welcome back to the ECE350 part 2 of lecture 4. So last lecture we talked about transmission line and also the parameters like resistance, inductance, capacitance and conductance, right? So there's all here: resistance per unit length, capacitance, inductance and conductance, right? So in this part we're going to try to model a transmission line using these parameters. To model transmission line, let's look at this one here. If we use a KBL, if I use a KBL for this transmission line, from this side to this side, if you use a KBL over here, so that's voltage over here. Let's say this is the supply, and voltage drop here, and also voltage over here will give you the KVL, right? So KVL over here, the voltage at the left hand side, and drop across the resistance. So the per unit, R prime is the per unit resistance. So you have to multiply by the distance to find the resistance times current, and same over here with inductance and the voltage on the other side, right? So now if I rearrange that, the equation will look like this. If I rearrange that, and if you know that if your delta t is small, right, then sorry, delta z is small, not t, delta z is small here, then this is because becomes a derivative, right? So you know that from the limits, so this becomes a derivative here, and is this side still stays the same, right? Now if I use the phasor notation, so VZT is the, if you get the real part of it with the complex part exponential, the real part over here, this is the phasor, right? So then I can replace this one with the phasor right here, right? And also on the other side, you know that di zt by dt in the phasor, it was j omega l times I phasor, right? So that's right here. So I can replace this one with j omega, right? J omega, it should not be L over here. Let me take the L out of here. It should be j omega, right? And L come from right here, right? So j omega L and your current in phasor domain. So this whole equation transfer into the phasor domain. So that's right here. So that's came from the KBL. If I take the KCL at this node over here, I'll go through this same kind of equation, we'll find this one. So these two equations are called telegrapher equations in phasor domain. So these both equations are modeling this part of the line. So line is only delta z long. It's a part of the line which is delta z long. That's why we have the per unit parameters of the line. All right, so these two equations are very important. We need to carry them forward. We're trying to find two things out of here. We have now in the equations, we have voltage, current, we have R, L, G prime and C prime. We're trying to find two other parameters from here. One is called characteristics impedance. Another is called propagation constant. So there's a goal here to find these two things: propagation constant and the characteristics impedance. So here, so now these two equations can be combined to find this one and this one here. These two equations are second order differential equations, and it has a gamma over there. So that gamma is called propagation constant. What is that gamma? That gamma includes all of your line parameters, R, L, G prime and C prime, right? So this one also a complex number. So it's a propagation constant. It has two part, real part and imaginary part. Real part is your attenuation constant. That means that will tell you how quickly your signal magnitude is decreasing, and beta is a phase constant. If you look at a signal at the same time, at the same time reference, at different parts of the transmission line, you'll see how the air differ in phase angle. So that's the beta. So beta is radian per meter, and attenuation constant is basically your how far you're going, and it's a dB per meter. Okay, all right. So with that, so now you have when a signal goes to transmission line, from source to receiver, it's called incident wave, and some of the wave reflected back from the receiving side is called reflected wave. So that's the two things over here. One going towards the load and then coming reflecting back from the load. So that's called reflected wave. So Now, to solve these two equations over here, if we have the solution for these two equations, proposed form the solution that I did here. So these are basically two things: a reflected and incident wave. So this part is your incident wave, this part is reflected wave, and same here. This part is incident, this part is reflected, right? So now if you model this one like with this right here, so this part is becomes a right now is admittance with inverse of impedance, and this is because this is basically your 1 over z0. A z0 is your characteristic impedance we're talking about, so that characteristic impedance also depends on your two things over here. R prime also, if you come over here, depends on all four parameters you have. So two things we are looking for the modeling is, one is gamma, which is propagation constant, and your z0, which is your characteristics impedance. All right, so why these two are important, from now on go forward we're going to use these two parameters to determine the line model. Okay, so two equations, one is this for the characteristic impedance, another one I saw in the previous slide, which is for the propagation constant. So we're going to do this problem in the class to apply those two equations into the problem. And we're going to go to the lecture 5 in the next slide. So again, remember that we, for the modeling of the line, we're looking for two parameters, which is propagation constant and the characteristic impedance.